Assalamu alaikum. This is our third lecture of Managerial Economics. Our today's topic is optimization with calculus. Before starting today's lecture, let's have a review of the previous lecture. In the previous lecture, we have discussed optimization process. Then we have discussed the relationship between the total, marginal and average concepts. And we have separately discussed in detail the revenue relations, cost relations and profit relations. So we'll continue with this topic, but today we are going to apply calculus while optimizing a function. The overview of today's lecture is we will discuss concepts of derivatives and marginals, concepts of derivatives, rules of differentiation, economic optimization with calculus. We'll also consider multivariate optimization. Then we'll introduce briefly partial derivatives and ultimately we will consider constrained optimization. Managerial decision making frequently requires one to find the optimum value of a function, that is a maximum value or a minimum value of a function. Now that value, as we have seen in our previous lecture, is the marginal value. We have seen that marginal value is delta y by delta x. That is, we have a function y function of x, therefore a change in x will bring about a change in y, and that change in x is denoted by delta x. And the resulting change in the dependent variable y is denoted by delta y. So that the ratio of delta y by delta x measures the slope of a function, which is in general we can say that this measures the slope of the function. The derivative is a precise measure of the slope of a function, and we have to see what's the difference between delta y by delta x and the mathematical definition of a derivative, that is dy by dx. Derivatives and marginal can be used interchangeably. That is, they are closely related in the sense that geometrically slope of a function at a point is actually the derivative of the function at that particular point. We have said that delta y by delta x is a measure of the slope, and when we change delta x, that is when we change the independent variable by 1 unit, the resulting change in y is denoted by delta y, and that gives us the slope of a function between any 2 points on the curve. When we make this change in x smaller and smaller, so that delta x is made smaller and smaller, the change in x is now less than 1. And we can show it by a graph. With the help of a graph, you can see in this slide points. We have located some points on the curve A, B, C and D. Look at the points B and D. Here we have drawn a chord or a line segment which is connecting any 2 points on the curve. Now to measure the slope of the curve between these 2 points, we use the formula delta y by delta x. As we change x from, let's say, x equal to 2 to x equal to 4, so that delta x at this point is equal to 2. Look at the line segment which we have drawn, which can be seen as line segment BC. Now the change in x, delta x is equal to 1. If we now draw another line which is smaller than this line, and we go on making this line smaller and smaller, that is the line which is called secant line or chord, which is connecting any 2 points on the curve. We make delta x smaller and smaller, and we say that delta x is approaching 0. But we are not saying that delta x is equal to 0. There is a difference between the two statements when we say delta x is equal to 0 and delta x is approaching 0. When delta x is approaching 0, the resulting change in y is now denoted by dy instead of delta x. That is, in order to distinguish between these two concepts, the measuring slope by the ratio delta y by delta x, and then taking the limiting value of delta y by delta x as delta x approaches 0, that is, as delta x is made smaller and smaller, so that now the geometrically this can be expressed as that the limiting value of the slope of a secant line is equal to the slope of the tangent line. As we can see on the graph, that this tangent line is touching the curve at a single point B. so that now we express this as mathematically we can express it as dy by dx is equal to the limit of the ratio delta y by delta x as delta x approaches 0. This is the mathematical definition of a derivative along a curve. It is on a particular point we are measuring the rate of change of the dependent variable y with respect to in an extremely small change in the independent variable x. As we can see that this means that the marginal value of a function or the slope of a function, geometrically it's the slope of the function, marginal value and derivative, we can use them interchangeably. That is, one is exactly, it is equivalent to the other. Marginal value is that can also be expressed in terms of derivatives dy by dx, that is the rate of change of the dependent variable with respect to a change in x, which is a very small change. In this slide we can see that we have drawn three curves. One is horizontal straight line, the other is a rising straight line, and the third one there we have drawn a non-linear curve. Now first of all, let's have a look at the curve which is drawn as a horizontal straight line. Here the function is y equal to 2, which is a constant function. That is, the value of y remains 2 regardless of the value of x. So in this case the slope of this function is equal to 0. Why? Because we are saying the slope of the function is measured as delta y by delta x, and in this case there is no change in y as such. Therefore delta y is equal to 0, so that the slope of this horizontal straight line is equal to 0. Now look at the mid panel curve where we have a straight line, and here the function which is drawn is y equal to 2x. As x increases, y also increases, so that we have a line which is, it is a straight line, but this time it is a rising line. The third function which we have drawn here is y equal to x square. And this is shown as a non-linear curve which is at its maximum when x is equal to 0. When x is less than 0, the slope of the function is also less than 0, that is negative. And when x is greater than 0, the slope of the function is also greater than 0, that is positive. With this background, now we are going to introduce some of the very simple differentiation rules. First of all, the derivative of a constant function. We have just now seen that the slope of a constant function, a delta y by delta x, we have seen that it is equal to 0, so that the derivative, that is dy by dx of this type of a constant function where y is equal to 2, or any other function where y is equal to any other constant value, let's say y equal to minus 100, the derivative will be equal to 0. Since here we are using simply dy by dx instead of delta y by delta x in order to distinguish between these two. Otherwise it is the limiting value of the ratio delta y by delta x as delta x approaches 0, so that dy by dx, or the derivative of a constant function, is equal to 0. The next rule that we have to consider is the power function rule, where the function is raised to some power. Let's say we have y equal to x raised to the power n. Then the derivative of this function will be dy by dx equal to n times x raised to the power n minus 1. In our example, for instance, here we have a power function which is y equal to, y is a function of x, and this is equal to a x raised to the power b, so that dy by dx is a b x raised to the power b minus 1. That is, the multiplicative constant is retained, and we simply have a, b is the exponent multiplied by the by x raised to the power 1 less than the original power. The next rule is sum difference rule. Here we have a function which appears as a sum of two functions. It is in the form u plus or minus v. Y is equal to u plus or minus v, where u and v are differentiable functions of x. The derivative of this type of function can be expressed as dy by dx is equal to the derivative of the first function plus or minus the derivative of the second function. Next we have the product rule of differentiation. Here the two functions appears as y equal to u into v. This is called u into v form. In this case the derivative is, we have two functions, that is u is a function of x and v is also a differentiable function of x, so that the function appears in the form u into v. The derivative is dy by dx is equal to the first function multiplied by the derivative of the second function plus the second function multiplied by the derivative of the first function. Next we consider the quotient rule of differentiation. Here the two functions, that is we have u and v, differentiable functions of x, and here the function appears as y equal to u by v. That is, u is the numerator and v is the denominator. So that dy by dx, in this case the formula that is used is v, that is the denominator, multiplied by the derivative of the numerator minus numerator multiplied by the derivative of the denominator, all divided by v squared, that is denominator squared. Next is the chain rule, that is function of a function rule. It is also called function of a function rule because here we are saying that y is a function of u and u in turn is a function of x. So that dy by dx is equal to dy by du into du by dx. In this case, as we can see that y is a function of x, y are the function g and f, because the first function says that y is a function of u and u in turn is a function of x. So whenever there is a change in x, this will bring about a change in u, and this in turn will bring about a change in y. So dy by dx is equal to dy by du into du by dx. Geometrically, we can see that the optimization with calculus, the derivative refers to the slope of the function, while that is the first derivative, or the simple derivative refers to the slope of the function, while the second derivative of the function refers to the change in the slope of the function. When we differentiate the same function, so suppose we have y function of x and its derivative is dy by dx, that is we have differentiated it with respect to x. Now if we differentiate this same function with respect to x again, that is what is called the second derivative of the function, so that we have differentiated the function with respect to x twice. As I was telling you that geometrically the derivative is the slope of the function, the second derivative, that is the first derivative, is the slope of the function, the second derivative is the change in the slope of the function. So when we maximize or minimize a function, we can see that here we have considered in our previous diagram that revenue is a function of q, where the revenue function was you have as you must have seen that the revenue function was rising, but first it was rising, then it attains its maximum, and thereafter it starts declining. Once it is rising, then when it is rising and we draw a tangent to the curve at that point, the slope of the tangent is positive, which is rising. When it attains its maximum point, at that point the slope of the curve is equal to 0. Why? Because now the tangent to the curve is a horizontal straight line, and we have already seen that the slope of a horizontal straight line is equal to 0. And thereafter the curve starts declining, that is when we draw a tangent to the curve at this point, its slope will be negative. We can summarize the optimization with calculus as given a function which is the objective function of the firm. The objective of the firm is to maximize revenue or maximize profit, and given a function y equal to f of x, then the first order condition is, which is a necessary condition, that we find the derivative and set it equal to 0. Then the second order condition is that the second order condition, which is a sufficient condition, is that we find the second derivative of the function and we see the results. If it is greater than 0, then x is a minimum point, and if it is less than 0, then in that case x is a maximum point. We have said that when the second derivative is greater than 0, we have a minimum point, and when the second derivative is less than 0, we have a maximum point. The reason is that as I have said earlier, that the second derivative tells us the change in slope of the function. So when we have a curve which is minimized, or which has a minimum point, you can see that the slope of the curve is negative, then it is stationary or 0, and afterwards it is increasing or it is positive. So the slope of the function which is attaining a minimum point is increasing. That is why we are saying that when the second derivative is greater than 0 or positive, we have a relative minimum point. Similarly, in the imagine a point which is a maximum, which is attaining a maximum point. In the neighborhood of the maximum point, first the slope is rising, then the slope is stationary, that is, it is equal to 0, and afterwards it starts declining. That is, the slope of this function which is maximizing is decreasing. That is why we are saying that the second derivative, when the second derivative is negative, the function or the point in question is a relative maximum point. Let's take an example to illustrate this optimization process. In this slide, as you can see that here we have total revenue function which is equal to 100q minus 10q square, and then we have taken the derivative of the function which is equal to, when we differentiate a total revenue function with respect to q, we get what? We get marginal revenue. And here this is equal to 100 minus 20q, and we set it equal to 0. This was our first order condition. First order necessary condition is that we find the derivative of the function and set it equal to 0. Once we get this point, that is, we get the marginal revenue function in this case, or the derivative of the function, which is 100 minus 20q equal to 0. Solving for q, we get q asterisk or q star equal to 5. This is called a critical value or a stationary value. That is, this is the point where the derivative, since we have set it equal to 0, this means that this is either a relative or a minimum, a relative maximum or relative minimum point. Now, to establish that whether this indeed is a relative maximum point or a relative minimum point, we use our second order condition, which is second order sufficient condition, in order to establish that the point in question is a maximum point or a minimum point. We find the second derivative of the function which is equal to minus 20. And as we can see that we have already said that when it is this is equal to negative, that is when the second derivative of the function is negative, less than 0, then the point in question is a relative maximum point. So at the output level of q equal to 5, the revenue of this firm is maximized. In the next example, we consider a function which is to be minimized. In this case, we have taken a marginal cost function. As you can see that the marginal cost function here is equal to 3q square minus 16q plus 57. Differentiating this function and setting it equal to 0, we solve for q which is equal to 2.67. And the second derivative of this marginal cost function is equal to 6, which is greater than 0. Hence, the function, this marginal cost function is minimized at q is equal to 2.67. In the next example, again, we will optimize a function. We are given total revenue function and total cost function. As we can see on the slide that we are given total revenue and total cost functions, we can find the optimum values by using two methods. One is the total method, and the other is in which we are using the marginal concepts. That is, the firm has to optimize its profits. So the profit function, as we know, is equal to total revenue minus total cost. That is, we subtract total cost function from the total revenue function and we get the profit function. We find the profit function and set it equal to 0, and we find its derivative, set it equal to 0, and we get a quadratic equation. Now look at the second method. By the second method, what we do here is that we differentiate the revenue function with respect to q and find the marginal revenue. And then we differentiate the cost function, that is the total cost function, and we find marginal cost function. And we know from our previous lecture that marginal profit is equal to marginal revenue minus marginal cost equal to 0. Or in other words, marginal revenue is exactly equal to marginal cost. So finding marginal revenue and marginal cost, in other words, differentiating these functions with respect to q, we then set them equal to 0 for our first order condition, and we get the same equation, that is a quadratic equation. Therefore, we can either use the first method or the second method, we will get the same results. Now here we have a quadratic equation. We can find the values of q which will maximize or minimize the function by using the quadratic formula, or we can use the factorization. In the next slide, you can see the quadratic formula. We can use either this quadratic formula or we can use factorization, and thereby we get two values of q, that is q equal to 1 and q equal to 4. Next, we find the second derivative of the function. In order to fulfill our second order condition, we find the second derivative function and then we substitute q equal to 1 and q equal to 4 in the second derivative function. As a result, we get the second derivative function here is minus 6 plus 15. At q equal to 4, the second derivative function is minus 9, which is less than 0. And at q equal to 1, the second derivative function, by substituting the value of q equal to 1 into the second derivative function, we get plus 9, which is greater than 0. Hence, we can see that the second derivative function is negative when q is equal to 4. This means that the firm is optimizing its profits when the level of output is equal to 4. And it is minimizing its profits when q is equal to 1, or in other words, it is incurring largest losses at this point when q is equal to 1. So far, we have considered a function of only two variables. That is, one is the independent variable and the other is the dependent variable. But in economics, we have many functions where we have more than one independent variable. That is, either the independent variables are two or more. For example, total revenue function here, we have considered that it is a function of q, that is the level of output. But there are other factors which can influence total revenue. For example, the advertising expenditure of the firm. So in that case, we'll have two independent variables. If in general we have, let's say, a function which is a function of three independent variables, that is x1, x2, x3, as you can see on the slide, that we have a function y, a function of x1, x2, x3. In this case, again, for optimization, we use the same procedure, but with the difference that now we have to find the partial derivatives. Instead of ordinary derivatives, we have to find the partial derivatives. Why the name partial? Because we are differentiating the function partially. If there are three independent variables, we will differentiate the function with respect to x1, with respect to x2, and with respect to x3. When we differentiate the function with respect to x1, we treat the other two independent variables which can influence the dependent variable. They are held constant. Similarly, when we find the partial derivative with respect to x2, the other two independent variables, that is x1 and x3, they are treated as a constant. As far as the rules of differentiations are concerned, we'll be using the same rules that we have already discussed today. The only difference here is that now we have more than one independent variable. And if it is a function of three variables or a function of two variables, then we have to find two partial derivatives or three partial derivatives. And using the same first order condition, we find the partial derivatives of the given function and then set them equal to 0, solve them simultaneously and get the optimum point. In order to illustrate the partial optimization or the optimization where we have a function, a multivariate function, we give an example here. We have to determine the value of x and y that maximize the following profit function. The profit function given is pi equal to 80x minus 2x square minus xy minus 3y square plus 100y. Solution steps are that we find the first partials with respect to x, with respect to y. The two independent variables in this case are x and y. So we partially differentiate the function with respect to x and with respect to y, set them equal to 0 and solve these equations simultaneously. As a result, we get the optimal value of x, which is equal to 16.52, and the optimal value of y is equal to 13.92. When we substitute these values of x and y into the profit function, we get the maximum profit, which is equal to $1356.52. Up to this point, we have considered optimization process without constraint. Now we are going to consider constrained optimization. In the real life, managers frequently have to face constraints. As you are well familiar with the constraints as far as the consumer is concerned. When consumer has to optimize his utility, then there are constraints. As you know, that the constraint is basically the budget constraint, that is the income of the consumer. For a producer or for a firm, there are many constraints such as quality constraints, then there are legal and environmental constraints. Similarly, there is the production capacity constraint. So in order to consider this constraint, now we have two methods to find the solution to a constraint optimization. One method is called substitution method, and the other method is called Lagrangian multiplier method. In the substitution method, what we do here is that we are given an objective function which is to be optimized. Obviously, when it is a cost function is to be minimized but subject to some constraint. Similarly, if it is a profit function or a revenue function, it is to be optimized, that is maximized, subject to some constraint. In order to make our problem simple, we have taken the same example here that we have used for the unconstrained optimization. The procedure, as far as the procedure is concerned, I said that we can use two methods. One is the substitution method, and the second is Lagrangian multiplier method. In case of substitution method, the constraint equation is transformed. We can, express it in terms of one variables, that is x in terms of y or y in terms of x. That value of the variable is then substituted into the original objective function, so that now we have reduced, sort of reduce the problem into an unconstrained optimization problem. That is, now since we have expressed x in terms of y and we substitute this value of x into the objective function, thereby we have reduced the function or equation into a single equation in a single variable. Then we find the derivatives as usual, set it equal to 0 and solve for the optimum value of the function. So in the Lagrangian function, on the other hand, which is a more powerful technique, we will consider here one example where first we will use the substitution method and then we will utilize the Lagrangian multiplier method. In this slide, you can see that we are giving an example to explain first the substitution method and then the Lagrangian multiplier method by using the same function. In this slide, you can see that we have a profit function which is to be maximized. The objective function is the profit function which is to be maximized, but here now we have the firm has to face a constraint in the form of x plus y equal to 12, which can be considered as, that is, the firm has to produce x plus y equal to 12, which can be considered as a production capacity constraint. So the firm has to optimize profit now with subject to some constraint, and in this case the objective function is a profit function and the constraint equation is also given. As I said earlier, that for the substitution method we have to express x in terms of y. So using the constraint equation, which is equal to x plus y equal to 12, we can rewrite it as x equal to 12 minus y. So that x is equal to 12 minus y, and now substituting this value of x into our original objective function, that is the profit function, we get an equation which is now a single equation in a single variable. So that in this case we can easily use the ordinary derivative, that is, we find the derivative of this function with respect to y, and we can set it equal to 0 and find the optimal values for x, y. And then by substituting those optimal values of x and y into the profit function, we can get the optimal value of the profit, that is the maximum profit that the firm can earn in this case. Now we substitute x equal to 12 minus y and into the profit function, and thereby reducing the profit function into a single equation, single variable. Profit function is equal to, as you can see on the screen, it is equal to minus 4y square plus 56y plus 672. Now differentiating this profit function with respect to y, we get d pi by dy equal to minus 8y plus 56, and setting it equal to 0, we can find the value of y. And here we have y equal to 7. Substituting this value of y into the constraint equation, we can easily find the value of x, which is equal to 5. And now substituting these values of x and y, which is where y is equal to 7 and x is equal to 5, into the original objective function, we will get the maximum profit which the firm can earn in this case, and that is equal to $868. Using same data, we are going to explain now the second method, which is the Lagrangian multiplier method. In this method, we have first of all to form the Lagrangian function. Lagrangian multiplier method is named after the mathematician Lagrange, and Lagrangian multiplier is simply a constant. In this method, first of all, we have to form the Lagrangian function. But before that, that is our first step, is to form the Lagrangian function. And that is simply the objective function plus lambda times the constraint. But before forming this Lagrangian function, we set our constraint equal to 0. That is, if it is in general, if it is given in the form gxy is equal to c, on the left hand side we have gxy, and on the right hand side we have c, which is the constant of the constraint. Then we when we rewrite it in the form c minus gxy is equal to 0. As I said that we are going to use the same data here, the same profit function, and this is to be maximized, be subject to the same constraint, that is x plus y equal to 12. So in this case, our first step is that we set the constraint equation in this form, that is, we set it equal to 0, and we rewrite it as 12 minus x minus y equal to 0. Then we multiply it by the Lagrangian multiplier, which is denoted by the Greek letter lambda. We can use any letter. It is not necessary to use lambda. We can use any other symbol for Lagrangian multiplier. So here we are using this Greek letter lambda as our Lagrangian multiplier. We multiply the constraint equation which we have set equal to 0 by lambda, and then add it to the original objective function. In this case, this objective function is the profit function, so that we get the Lagrangian function, and it is equal to the objective function plus lambda times the constraint. This method is considered to be a very powerful technique to find the constraint optimization, that is, to solve a problem which is subject to some constraint. The reason is that here we are solving for the Lagrangian function, and as a result of forming this Lagrangian function, we will see that since we have set the constraint equation equal to 0, therefore we will the value that we will get as a result of the solution of this problem, that will be the optimal value, which is optimal value for the Lagrangian function as well as for the objective function, which was our original objective function. So that the optimal value for the Lagrangian function and the objective function is identical, because the reason is that we have set the constraint equation equal to 0, and thereby it will also fulfill or satisfy our constraint. Now look at the example here. We are given the profit function, which is equal to 80x minus 2x square minus xy minus 3y square plus 100y, subject to the constraint x plus y equal to 12. We set it in the form, first of all, we rewrite our constraint equation as 12 minus x minus y equal to 0. We multiply it by lambda, and then we add it to the original objective function. Once we form this Lagrangian function, the next step is to find the partial derivatives with respect to x, y, and lambda. Now, we have said previously that lambda is a constant. At this point, we are treating it as a variable, so that now will have three equations in three variables, that is x, y, and lambda. We will differentiate the Lagrangian function with respect to x, with respect to y, and then with respect to lambda, and set all these equations or partial derivatives equal to 0. Once we set them equal to 0, we can solve these equations, three equations in three variables simultaneously, and get the value of x, y, and lambda that will maximize the profit of the function. From the first two equations, if we subtract the second equation from the first equation, we will eliminate lambda from the two equations. As a result, we will get an equation which is labeled as equation 4, which is in two variables. And the third equation, that is the third partial derivative, as we can see that this is always where we have differentiated the Lagrangian function with respect to lambda. This is always equal to the constraint equation. Now, solving the third equation and the fourth equation simultaneously will get the value of y, which is equal to 7. When we substitute this value of y, which is equal to 7, into our constraint equation, that is in this case it is the third equation or the third partial derivative, we will get x equal to 5. Now this you can see here that x is equal to 5 and y is equal to 7. We have obtained the same result while using the first method, that is the substitution method, but here we also have lambda. Substituting x equal to 5 and y equal to 7 into either the first equation or the second equation, we will get the value of lambda, which is in this case equal to 53. As I said earlier, that this method or the Lagrangian multiplier method is a more powerful method than the substitution method, in the sense that sometimes it is not possible to express one variable in terms of the other variable, and sometimes it becomes very tedious to use substitution method. So in that case, we use the Lagrangian multiplier method. The other reason is that lambda, which is the Lagrangian multiplier method, it has an economic interpretation. It has an important economic interpretation, that is, it has an economic meaning. Now let's see what is meant by this statement. What are we referring to by this statement? We are saying that lambda has an important economic interpretation. In this case, as we can see, the value of lambda is 53. If we substitute x equal to 5 and y equal to 7 into our original objective function, we get the maximum profit, which is $868. And similarly, if we substitute these values, that is x equal to 5, y equal to 7 and lambda equal to 53 into the Lagrangian function, we'll get the same value, that is same maximum profit, that is $868. As I said earlier, that by substituting the optimal values of our two choice variables, in this case x and y, into either the objective function, which was the original objective function, or the Lagrangian function, it will be, the value will be identical. This means that it is not only satisfying the Lagrangian function but also satisfying the original objective function, and at the same time it is satisfying the constraint equation, because we have incorporated the constraint equation into the Lagrangian function, but before adding it to the Lagrangian function, we have set it equal to 0. Thereby, it is also satisfying the constraint of the firm. In our example, the value of lambda is equal to 53. When the constraint of the firm is relaxed, that is, suppose in our case it was x plus y equal to 12. If now the constraint is increased, that is from x plus y equal to 12, it is now x plus y equal to 13, so that the constraint of the firm is relaxed and it is increased by 1 unit. It has an impact on the optimal value of the objective function. In this case, we have obtained that the maximum profit is $868 when the firm is producing 5 units of x and 7 units of y. If we now relax our constraint by 1 unit, that is, now the new constraint is x plus y equal to 13, this will increase the profit of the firm by lambda times. That is, now the new profit of the firm will be $868 plus 53, which is the value of the lambda. In that sense, we can say that the value of lambda has an important economic interpretation. It is the marginal effect on the objective function solution associated with a 1 unit change in the constraint. To generalize, we can say that Lagrangian multiplier lambda in this case indicates the marginal effect of decreasing or increasing the constraint requirement by 1 unit. this will decrease or increase the optimal value of the objective function by lambda times. So we can say that this concept of Lagrangian multiplier method, it helps the managers to evaluate the potential benefit or cost of relaxing constraint. So in today's lecture, we have examined the relation between a marginal value, a derivative, and the slope of a function. As we have seen that we can interchangeably use the terms derivative or marginal value, and graphically or geometrically we can express the same as the slope of the function. We have considered the optimization process, and we have first considered the unconstrained optimization, and we have considered a function where it is a function of only a single variable, so that we have a univariate variable. और वहाँ पे हमने जो है फर्स्ट ऑर्डर कंडीशन यूज़ की और सेकेंड ऑर्डर कंडीशन की यूज़ की. By finding the first derivative and setting it equal to 0, we have found the candidate maximum or minimum point, and we have thereby we find the critical value, that is the value of the independent variable that maximizes or minimizes the objective function. Next, we have seen that the first derivative or the derivative of a function is simply, it is the slope of the function or the rate of change of one variable with respect to the other variable, the rate of change of the dependent variable with respect to the independent variable. Using our first order condition, we have found the critical value, and then by using the second order sufficient condition, that is by finding the second derivative of the function, we have established the difference between the maximum point and the minimum point. That is, we have been able to use the second order sufficient condition. We have been able to distinguish between a maximum point and a minimum point. Next, in today's lecture, we have considered multivariate functions. That is the optimization of a multivariate function. And we have seen that many economic relations or functions, they are not a function of a single independent variable. There could be two or more independent variables. And in that case, we have to use partial derivatives. And we have seen that for partial derivatives, we have to differentiate the function partially, treating all the other variables as constants. As far as the procedure of optimization is concerned, it is the same. That is, we find the partial derivatives of the objective function, set them equal to 0, and find the critical value or the candidate maximum or minimum point. So far, up to that point, we have considered optimization or optimizing a function, that is either maximizing or minimizing without constraint, that is unconstrained optimization. And in the end, we have considered constrained optimization, because in the real world, it is both the economic agents, be it consumer or the producer, they have to face constraints. And this means that they have to optimize a function subject to some constraint. The constraint could be a quality constraint, a legal constraint, or an environmental constraint. It's quite obvious that the constraint increases the cost of a firm. That is, it adds to the cost of the firm. So in our example, we have seen that we have taken the same example, the same profit function, and we have optimized it unconstrained and then with some constraint. We have seen that for unconstrained optimization, the value of the maximum profit was $1,200 something, but using the same profit function subject to a constraint, where the constraint equation was x plus y equal to 12, which can be considered as a production capacity constraint, we have seen that the value of the maximum profit has declined. That is, it is reduced from $1,200 something to $868. This means that constraint always adds to the cost of the firm. In order to solve a constraint optimization problem, we have used two methods. One is the substitution method, and the other is Lagrangian multiplier method. In the substitution method, we are given an objective function subject to some constraint. We use the constraint equation and we express one variable in terms of the other variable, and then we substitute this value of the variable into the original objective function, so that we reduce the objective function into a single equation in a single variable. And in this case, instead of partially differentiating the function, we can also differentiate it using the ordinary derivative, because now it is only one variable case. So we find, or we differentiate this function, and we get, as a result, we get the critical value of the function. That could be a possible maximum point or a minimum point. That is, we get the value of one variable, and then we substitute that value of the variable into the constraint equation to get the value of the second variable, so that we solve this system and we get the optimal values of the two commodities, that is X and Y. And once we get these optimal values, we substitute these values into the objective function to get the maximum profit that the firm is earning. To use the second method, sometimes it is difficult to express one variable in terms of the other variable, and also the second method is a more popular method. The reason is that it is a powerful method as compared to the substitution method. In that case, we use the Lagrangian multiplier method. The Lagrangian multiplier is a constant, and we simply form the Lagrangian function. This is the first step. And but before forming the Lagrangian function, we express our constraint equation as we set it equal to 0. So that if it is given gxy is equal to c, we set it as c minus gxy equal to 0. We set it equal to 0, we multiply it by lambda, and then we add it to the original objective function, and thereby we form the Lagrangian function. The second step is to find the partial derivatives of this Lagrangian function with respect to all the variables. That is, in this case, the choice variables are 2, that is X and Y. And now we differentiate the Lagrangian function with respect to X, with respect to Y, and with respect to lambda. That is, here we are treating lambda as a variable now. We get 3 equations in 3 variables. In our case, in our examples, we had 3 equations in 3 variables. Then we solve these equations simultaneously to get the optimal values of X, Y, and lambda. In our example, the optimal values of X is 5, Y was equal to 7, and lambda equal to 53. We substitute these values of choice variables into the original objective function, and we get the maximum profit. And in this case, that was equal to $868. As we have already seen that the value of lambda has an important economic interpretation. If we now relax our constraint equation, that is, if we increase the constraint by 1 unit or we decrease the constraint by 1 unit, this will increase the optimal value of the objective function by lambda times. And in this case, since the value of lambda is 53, then the maximum profit will be $868 plus $53. And if, on the other hand, we tighten our constraint, that is now X plus Y equal to 11, that is the new constraint of the firm, in that case, the value of the objective function, that is the optimal value of the objective function, which in this case is $868, this will be decreased by lambda times, that is 868 minus 53. This is how we solve an unconstrained optimization problem and a constrained optimization problem. Next time, our discussion topic is demand analysis. With that, we come to an end of this session. Thank you. Khuda Hafiz.